Hello and welcome yet again in a place and a time. We shall see if the truth holds dear. I got a lot of coffee. This works perfectly. This also works perfectly. Okay, silence. Silence. Let me set up the stream and drink some coffee and begin the journey of classical mechanics. See, we decided upon 1 second. (8:12). This is 8:12. So, we are gonna go to the syllabus lectures, 2 sessions a week, 1.5 hours a session. Recitations. Okay, it's the advanced first year. Okay. 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 Calendar. Problem set. Readings. We are reading this. Chapter 1, 2, 3, 4, 5, 5 not, 6, 7, 7 and 8, 8, 9, 11. Okay. We're gonna copy this book over. Assignments. Problem set. Let me see the problem sets. Okay. Projects, related researchers, exams. Exams. Okay. Now let us go into physics day 2 and type physics day 2. Something is wrong with my tablet, so I should unplug it. Unplug it. Unplug it and plug it. Let's see if it works now. Perfectly it works. Okay, so chapter 1 it said. readings. Vector and Intro and Vector Definitions, Chapter 1. Okay, so we just go read. Okay, this is not necessary. A preface. There is a good reason for the tradition that students in science and engineering start college physics with the study of mechanics. Mechanics is the cornerstone of pure and applied science. The concept of energy, for example, is essential for the study of the evolution of the universe, the properties of elementary particles, and the mechanisms of biochemical reactions. The concept of energy is also essential to the design of a cardiac pacemaker and to the analysis of the limits of growth of industrial society. However, there are difficulties in presenting an introductory course in mechanics which is both exciting and intellectually rewarding. Mechanics is a mature science, and satisfying discussion of its principles is easily lost in superficial treatment. At the other extremes to enrich, yes, enrich. Let me just put my comments up. So, top chat and live chat. Thank you. To enrich the subject by emphasizing advanced topics can produce a false sophistication which emphasizes technique rather than understanding. This text was developed from the first year course which we taught for a number of years at the Massachusetts Institute of Technology and earlier at Harvard University. We have tried to present mechanics in an engaging form which offers a strong base for future work in pure and applied science. Our approach departs from tradition more in depth and style than in choice of topics. Nevertheless, it reflects a view of mechanics held by the 20th century physicists. Our book is written primarily for students who come to the course knowing some calculus, enough to differentiate and integrate simple equations, functions. It has also been used successfully in courses requiring only concurrent registration in calculus. Of course, uh, uh, for a course of this nature, Chapter 1 should be treated as a resource chapter, deterring as detailed discussion of vector kinematics for time. Okay, yada yada yada. I understand. I am pretty certain I understand this. To the ether, the first 8 chapters. Okay, okay, all right. Vectors 1. Vectors and kinematics. Kino introduction. The goal of this book is to help you acquire a deep understanding of the principles of mechanics. The subject of mechanics is at very heart of physics. Its concepts are essential for understanding the everyday physical world as well as the phenomena of the atomic and cosmic scales. The concepts of mechanics such as momentum, angular momentum, and energy play a pivotal role, a vital role, in practically every area of physics. We shall use mathematics frequently in our discussion of physical principles, since mathematics lets us express complicated ideas quickly and transparently, and it often points the way to new insights. Furthermore, the interplay of theory and experiment in physics-based on quantity prediction and measurement. For these reasons, we shall devote this chapter for developing some necessary mathematical tools and postpone a discussion of the principle of mechanics until chapter 2, vectors. Vectors. The study of vectors provides a good introduction to the role of mathematics in physics. 1 second. Boop. Good. Mathematics in physics. By using vector notation, physical laws can often be written in a compact and simple form. As a matter of fact, modern vector notation was invented by a physicist, William Gibbs of Yale University, primarily to simplify the appearance of equations. For example, here is how Newton's second law, which we shall discuss in the next chapter, appears in 19th century notation. Fx equals ma ax. Fy equals may, Fz equals maz. In vector notation, one simply writes F equals ma. Our principal motivation for introducing Gibbs, fantastic work. I'm not sarcastic at all. Our principal motivation for introducing vectors is to simplify the form of equations. However, as we shall see in the last chapter of the book, vectors have a much deeper significance. Vectors are closely related to the fundamental ideas of symmetry, and their use can lead to valuable insights into the possible forms of unknown laws. Okay. Vectors can be approached from 3 points of view: geometric, analytic, and axiomatic. True, all 3 points of view are useful. We shall need only the geometric and analytic approaches in our discussions of mechanics. From the geometric point of view, a vector is a directed line segment. In writing, we can represent a vector by an arrow and a label, in the latter capped by a symbolic arrow. In print, bold-faced letters are traditionally used. In order to describe vectors, we must specify both in length and in direction. Unless indicated otherwise, we shall assume that parallel translation does not change a vector, thus the arrows are left all represented the same vector. If two vectors have the same length and the same direction, they are equal. These vectors B and C are equal. They are equal. I agree. The length of a vector is called its magnitude. The magnitude of a vector is indicated vertical bar if no confusion will occur by using italics. For example, the magnitude of A is written as A bar. By using italics, for example, the magnitude of A is written A bar or simply cross A. If the length of A is the square root of 2, then A is equal to square root of 2. If the length of a vector is 1 unit, we call it the unit vector. A unit vector is labeled by a caret. The vector unit length parallel to A is A squiggly. It follows that A squiggly is equal to A divided by A italic. A squiggly is equal to A divided by A italic. And conversely, A is equal, and conversely. Okay. The algebra of vectors. Multiplication of vectors by a scalar. If we multiply a positive... 1 second. Okay. Multiplication of vectors by a scalar. If we multiply by a positive scalar b, the result is a new vector cba. The vector c is parallel to a and its length is b times greater. The c equals a and b equals I understand. The result of multiplying a vector by -1 is the vector has the opposite in direction, anti-parallel to the original vector. Multiplication of vector by a negative scalar evidently can change both the magnitude and the direction sense. Addition of two vectors. Addition of vectors has been a simple geometrical interpretation shown by the drawing. The rule is to add vector b to a, place the tail of b at the head of a, the sum is a vector from tail of a to the head of b, subtraction of vector. Since a minus b is equal to a plus minus b, in order to you do that. Okay, we know this. We know this. Scalar dot product. The first type of product is called a scalar product, since it represents a way of combining two vectors from a scalar. The scalar of a and b is denoted by a dot b and is often called the dot product. A dot product b is defined by a dot b a b cos phi, where phi is the angle between a and b, where they are drawn tail to tail. Okay, we will write this for some reason. AB is equal to AB cos phi. Okay, perfection. And that's about it. Laws of cosines. C equals A plus B. C equals C, I plus B, A plus B. C squared is equal to A squared plus B squared times 2AB cos phi. The result is generally expressed in terms of angle phi. C squared is equal to A squared plus B squared minus 2AB cos phi. We have used cos phi is equal cos pi minus phi equals minus cos phi. Okay. Work and the dot product. The dot product finds its most important application in the discussion of the work and energy chapter 4. As many have already known, the work done by a force on an object is displacement d is the object times the component F along the direction d. If the force is applied at an angle theta at the displacement, the work is equal to F cos phi times d. Granting for the time being that the force displacement vector is equal to work is equal to F dot product D. Now the cross product. Thank you. Vector product. The second type of product we need is the vector product. In this case, two vectors A and B are combined to form a vector C. The symbol of a vector product is the cross. C equals A cross B, where the alternative name is the cross product. The vector product is more complicated than the scalar product because we have to specify both the magnitude and the direction of A cross B. The magnitude is defined, it follows C A cross B. Then C is equal to A B sinus phi, where phi is the angle between A and B, where they have drawn tail to tail. To eliminate ambiguity, theta is always taken as the angle smaller than pi. Note that a vector product is 0 when theta equals 0 or pi, even if A and B are not 0. Where we draw A and B tail to tail, they determine a plane. We define the direction of C to be perpendicular to the plane A and B, A, B, and C form what is called a right-hand triple. Imagine a line, a right-hand coordinate system with A and B in the XY plane as shown in the sketch. A lies on the x-axis, B lies towards the y-axis. If A, B, and C form a right-hand triple, then C lies on the z-axis. We shall always use the right-hand coordinate system, such as the one shown on the left. There is a way to that. Here is another way to determine the direction of the cross product. Think of a right-hand screw with the axis perpendicular to A and B, rotated in the right direction, which swings A into B. C lies in the direction of the screw advances. Warning, be sure not to use the left-hand screw. Fortunately, they are rare. Hot water faucets are among the chief offenders. Your honest everyday wood screws is right-handed. As a result of our definition of the cross product is that B cross A equals minus A cross B. Here we have the case in which the order of multiplication is important. The vector product is not commutative. In fact, since reversing the order reverses the sign, it is anti-commutative. We'll see that A cross A equals 0 for any vector A. Yeah, why not draw the screw? Because I always forget this shit. Wow. This is C. This is B. This is A. Doesn't matter. Examples of vector in physics. The multiple physics. Yeah, we know this one. We know this one. We know this one. Areas of vector. We know this one as well. Components of a vector. Right. Vector. Okay. Components of a vector. The fact that we have discussed vectors without introducing a particular coordinate system shows why vectors are so useful. Vector operations are defined without reference to coordinate systems. Oh. All right. Okay. Okay. Vector algebra, example 1.5. Let's see. Let vector 3, 5, minus 7, 2, 7, 1. Find A plus B, A minus B, A, B, A dot B, and the cosine of the angle between A and B. The first one is easy. The second one is easy. The third one is easy. The fourth one is easy. The fifth one is easy. And the sixth one is A times B, which we will note. We will note that this B cosine A B is equal to A B italic A italic B. All right. Okay, base vectors, we know base vectors. We definitely do. Displacement and the position vector. Okay. Okay, we do know that. Velocity and acceleration. Alright. We can write this as v is equal to the limit of t going to 0 of x times t plus delta t minus xt divided by dt. Okay, same for a motion in several dimensions. Okay, okay. Alright. Finding v from r. The position of a particle is given by r is equal to a, which is some constant, I would assume, e to the alpha divided by I plus e to the minus alpha divided by j, where alpha is a constant. Find the velocity and sketch its trajectory. Okay, v is equal to dx dt. We have that. Um, yeah, that's just a dt. Um, where is where is the time? Oh, it has time. Oh, it has time. It's not divided by. It's dt. So we do that and we get the same answer for that. Just alpha popping out. V is equal to a. Vy is equal to a. Okay, the magnitude of v is equal to vx squared plus vy squared and a half. Okay, to the half to the root. In the sketching of motion point, it is usually helpful to look at the limiting cases. A equals t0, we have a I plus j, a alpha I minus j. Caution, we cannot neglect. Okay, and this is the trajectory. Okay. As t approaches 0, its limit becomes that, which is a vector along the x-axis, and v is equal to that. The speed increases without limit. Okay. Similarly, the acceleration is defined by that. We could continue to form new vectors by taking higher order derivatives where, as we shall see in our study of dynamics, that r, v, and a are chief interest. Of chief interest. Okay. Next. Uniform circular motion. Circular motion plays an important role in physics. Here we look at the simplest and most important case, uniform circular motion, which is circular motion at a constant speed. Consider a particle in the xy plane according to the r equals r cosine omega L I sinus omega L j, and the acceleration that, using the familiar identity sin, we have that r is constant. The trajectory is a circle. The circle moves counterclockwise around the circle, starting from the r0 at t, which is called an angular velocity of the motion, is measured in radians per second. T, the time required to execute one complete cycle, is called the period. V equals dx or dt, and when you compute that, we show that v is tangent to the trajectory by calculating v times r, and there we have omega times r is equal to v. Since v is perpendicular to r, it is tangent to the circle, and as we expect, incidentally, it is easy to show that r omega equals constant equals v. A is equal to minus omega squared r. Okay, we know this. We know this. A word about dimensions in units. Physical. Thank you, Anya Vanyevich. Physicists call the fundamental units in quantity is measured the dimension of the quantity. For example, the dimension of velocity is the distance time. The dimension of acceleration is velocity time. For example, distance over time equals distance over time squared. As we shall discuss in chapter 2, mass, distance, and time, and the fundamental physical units used in mechanics. To introduce a system of units, we specify the standards of measurement for mass, distance, and time. Okay. The natural unit for measuring an angle is a radian. The angle theta is in radians s divided by r, where s is the arc subtended uh, by theta in a circle of radius r. Theta is equal to s divided by r. 2 pi radians is equal to 360 degrees. We shall continue to use radians as the unit of angle unless otherwise stated. For example, in sinus Vt is in radians. V therefore has the dimensions of 1 over time and the units radians per second. The radian is dimensionless, since it's the ratio of two lengths. To avoid gross errors, it is a good idea to check that both sides of the equation have the same dimensionality of or units. For example, the equation v equals that is dimensionally correct, since exponentials and their arguments are always dimensionless. Alpha has the units 1 over second, and the right hand side has the correct units meters per second. Okay, let's go. Formal solution for kinematic equations. Dynamics, which we shall talk in the next chapter, enables us to find the acceleration of the body directly. Once we know the acceleration, finding the velocity and the position is a simple matter of integration. Here is the formal integration procedure. If the acceleration is known as the function of time, the velocity can be found from the defining equation. dv of t divided by dt is equal a of t. By integration with respect to time, suppose we have to find v of t given the initial velocity v of t0 and the acceleration a of t. Dividing the time interval t1 minus t0 into parts n, delta t is equal to t1 minus t0 divided by n. Okay, then it goes into that. The approximation becomes exact in the limit n goes to infinity, delta t goes to 0, and the sum becomes an integral. Vx of t is equal to Vx of t0 plus the integral of t0 to t1 ax or dt. Okay. The y and z components can be treated similarly, combining the results we get at. Okay, makes sense. I already did this. I didn't fail the exam. I passed the exam, so it's really I'm trying to get just to learn a bit more about this and then see how much I forgot. Okay. Finding the velocity from acceleration v0 taking these equations in turn and the given values of v0 and a, we can obtain t equals 5 seconds. Okay. Position is found by second integration, starting with dx of t divided by t is v of t. We find the argument identical above. Okay. A particularly important case is the uniform motion. Is a test of uniform acceleration. If we take a constant t0, we have v equals v0 plus at, and r of t is equal to r0 plus the integral of v0 plus a of t dt. So the r of t is equal to r of 0 v of 0 t plus 1.5 a of t squared. Quite likely you're already familiar with this, its one-dimensional form. For instance, the x component of the equation is x0 plus v0t plus 1/2 at squared, where v of the x is a component. This expression is so familiar to me independently apply to general case of varying acceleration. Don't. It only holds for uniform acceleration. In general, the full procedure described above must be used, obviously, because if it depends on a different type of t, not on a constant t, then the t changes. Suppose that an object moves freely under the influence of gravity so that it has a constant downward acceleration g. Choosing the z-axis vertically upward, we have a is equal to minus gk. If the object is released, t equals 0 with initial velocity v0, we have x is equal to x0 plus v0 xt, and so for all the others except for z, where we have the influence of gravity, which is 1/2 gt squared. Without the loss of generality, we can let r 0 and assume that v is also 0. The latter assumption simply means that we choose the coordinate system so that the initial velocity with the zx plane is 0. Then zx is equal to v naught xt, and z is equal to v naught xt minus 1/2 g t squared. The path of the object is shown in a sketch. We can eliminate time from the equations x and z to obtain the trajectory, which is z is equal to v0x divided by v0x, x minus g divided by 2v0 squared x squared. This is a well-known parabola of free fall projectile motion. However, as mentioned above, the uniform acceleration is not the most general case. Okay, that's to be known. Non-uniform acceleration, the effect of radio wave on isotropic ionospheric electron. Okay. The ionosphere is the region of electrically charged gas composed of positively charged ions and negatively charged electrons, which surrounds the Earth at a height of approximately 200 kilometers. If a radio wave passes through the ionosphere, the electric field accelerates the charged particle. Because the electric field oscillates in time, the charged particles tend to jiggle back and forth. The problem is to find the motion of the electron of the charge, minus E, at the mass m, which is initially at rest, and which suddenly subjected to an electric field E is equal to E0 sinus omega t. Omega is the frequency of oscillation in radians per second. T is the time. The law of the force for the charge of electric field is F equals minus E, and by Newton's second law we have A is equal to F divided by M equals minus E divided by M. If the reasoning behind this mystery this is a mystery to you, ignore it for now. It will be clear much later. This example is meant to be a mathematical exercise. The physics is an added dividend. We have A is equal to minus E divided by M is equal to minus V E0 divided by M sinus omega t. E0 is a constant vector as we shall choose for a coordinate system so that the x lies along it. Since there is no acceleration in the y or z directions, we need to consider only the x motion. With this understanding, we can drop subscripts and write A for AX. X. Okay. A of t is equal to minus E0 divided by M sinus omega t. A0 sinus omega t. Where A0 is minus EE0 divided by M. Then Vt is equal to V naught, the integral of A of t dt. We do that, we do V naught minus A0 divided by omega cosine omega t from 0 to t is equal to omega V0 V0 A0 minus A0 divided by omega cosine omega t minus 1. And x is equal to x naught plus omega v t dt. We put that in, we get x0 is equal to omega 0 plus a0 divided by v omega times t, which is a0 divided by omega squared sinus omega t, where we are given that x is 0 and v0 are 0, so we have x is equal to a0 divided by omega times t minus a0 divided by omega squared sinus omega t. The result is interesting. The second term oscillates. It corresponds to the jiggling motion of the electron, which we predicted. The first term, however, corresponds to the motion with uniform velocity. So in addition to the jiggling motion, the electron starts to drift away. Can you see why? I can't see why. Just says it in a fucking formula. You calculated it. Shut up and calculate. I'm joking. Please don't do that. More about the derivative of a vector. In secondary, we demonstrated how to describe velocity and acceleration by vectors. In particular, we showed how to differentiate vector r to obtain a new vector v dr dt. We want to differentiate other vectors with respect to time in that occasion, and so it is worthwhile generalizing our discussion. We sometimes want at, which is a function in time, the change a during the interval t to t plus t delta t is a is a is a complete analogy to the procedure we follow differentiating r in second. We define the time derivative of a by dA dt equals limit of a blah 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 blah. Good. It is important to appreciate that a dA divided by dt is a new vector which can be large or small and can point in any direction depending on the behavior of a. There is one important respect in which dA dt differs from the derivative of a simple scalar function. A can change in both magnitude and direction. A scalar function can change only in magnitude. This difference is important. The figure illustrates the addition of a small increment dA delta A to A. In the first case, delta A is a parallel to A. This leaves the direction unaltered but changes the magnitude. In the second, dA is perpendicular to A. This causes a change in direction but leaves the magnitude practically unaltered. Good. In general, A will change in both magnitude and direction. Even so, it is useful to visualize both types of change taking place simultaneously. In the sketch to the left, we show a small increment delta A resolved into a component factor delta A parallel to A and a component factor delta A perpendicular to A. In the limit where we take the derivative, delta A changes to the magnitude of A but does not not its direction, which delta A tangential changes the not tangential prob mm, not tangential, the head-on changes direction delta A but not its magnitude. Students who have now clear understanding of the two new ways a vector can change sometimes make an error by neglecting one of them. Instance, if dA dt is always perpendicular to A must rotate since its magnitude cannot change. It is time dependent arises solely from the change of direction. The illustrations below show how rotation occurs when delta A is always perpendicular to A. The rotation motion is more made apparent by the drawing. Okay. Okay. The following is an example of the idea of rotating vectors to circular motion. Okay. Whew. Let's go. Given by r cos omega t L plus omega t J. The velocities cos the possible change show yes. This means that the velocity constant so it must rotate to time. So the V is steadily seen from sketch which shows V at various positions along the trajectory. In the second sketch, the same velocity vectors are drawn in a common origin. It is apparent that each time a particle completes its traversal, the velocity vector is swung around a full circle. Perhaps you can see what the acceleration rate also undergoes uniform rotation. Suppose a vector A of t has constant magnitude A. The only way AT can change its time is by rotating, and we shall now develop a useful expression for the time derivative dA dt of such a vector, rotating vector. The direction dA dt is always perpendicular to A. The magnitude dA dt has been found the following geometrical arguments. The change in A is the time interval t to t plus t delta t. Is delta A equal A t plus delta t minus A of t, using the angle A theta defined in the sketch. Italic delta TA is equal to 2A sinus delta theta divided by 2. Okay, it's hard to read it all. It's hard to read it all. Okay, simple application result, frame, returning to the general case, result of rotation can change in magnitude. Okay, sufficiently small, divided by the t, take the limit. Okay. Now polar coordinates, that's the kicker. Rectangular or Cartesian coordinates are well suited for describing motion in straight line. For instance, if we orient the coordinate system so that one axis lies in the direction of motion, then the one single coordinate changes as the point moves. However, the rectangular coordinates are not always useful for describing circular motion, and since circular motion plays a prominent role in physics, it is worth introducing a coordinate system more natural to it. We should mention that although many coordinate systems we like, the proper choice of the coordinate system can vastly simplify a problem, so that the material in this question is very much in spirit of the advanced physics. Quite likely some of this material will entirely be new to you. Be patient if it seems strange, even if it's difficult at first. Once you have studied the examples and worked a few problems, it will seem much more natural. Our new coordinate system is based on cylindrical coordinate system. The axis z on the cylindrical system is identical to the Cartesian coordinates. However, the position in x and y plane is described by the distance r from the z-axis and the angle theta that r makes with the z-axis. These coordinates are shown in the sketch, and that's the sketch, and that's the truth. Okay. Well, I know how that works. Okay. Okay. Next. Okay. Okay. Now this is gonna be a nightmare to do. But yeah, I'm so tired. Shouldn't have overworked myself. I'm gonna start the tomorrow stream earlier. I've decided. And we will end this one at 12. I'm too tired. Acceleration of polar coordinates. I mean, I'm listing off what I already know. So I'm sorry if you don't. This is kind of my. I do know this. Except this is utter insanity. But yeah. Taylor series, we know that. We do know that as well. We do know that. Okay. Some reference calculus text. Okay. Problems. Get to problems. We are gonna glance at them. See if we can do it. Perhaps not. We know the first one. We know the second one. We know the third. We know the fourth one. Fifth one is probably easy. Okay. Now we are at proper stuff. Our aim in this chapter to understand Newton's laws of motion. This is a modest task. Okay. Thank you for the modest task. I can feel the motion. I understand this. I definitely understand this. Okay. I understand this. I probably need something I already don't know. And this is it. This is it. This is it. Let's go by example. The astronauts initially at rest in free space pull on either end of the rope. Astronaut Alex played football in high school and is stronger than us. Was chest. The maximum force with which Alex can pull is larger than the maximum force which Bob can pull. The maximum mass of the rope is negligible. Find their motion if each pulls the rope as hard as he can. Okay. Okay. I know this. Okay. A freight train. Classical. A wedge. I know wedge. I know this as well. Currently. This I do know as well. Block on a string. Now this is complex. That's what rules constant. we're gonna stop here, and tomorrow 13 tomorrow 13 I'm gonna do more streaming. I'll literally do nothing. I'll stop here. I need, oh, tier listing dinosaurs. They didn't update my stream. Doesn't matter.